In this series of lectures, we're going to talk about bond strength, and we're going to come back to ionic compounds and talk about both ionic and covalent compounds for this part. So let's start with covalent bond strength. It's really measured by the amount of energy that it takes to break 1 mole of a bond in a compound. And we call this bond energy or bond enthalpy. See, we brought enthalpy back from chapter 5. So when it takes energy to make a chemical reaction go because we're breaking bonds, that's our bond energy. This also goes back to how we talked about potential energy being stored in chemicals as chemical energy. And so that bond energy is the amount of energy it takes to overcome the potential energy stored in the bond between the two atoms. So bond energies are measured and reported in the gas state only. We are also talking only about homolytic cleavage. And like, what does that mean? So homolytic cleavage is when, let's take our hydrogen and fluorine bond. That line represents 2 electrons. A homolytic cleavage is referring to splitting this bond. So 1 electron stays with the fluorine and 1 electron stays with the hydrogen. And so if we broke it homolytically, we would have a hydrogen with 1 electron and a fluorine with 7 instead of 8 valence electrons. Heterolytic cleavage is when you have both of the electrons stay with one of the elements and the other element gets nothing. But our bond energies are only going to be looking at homolytic cleavage. So these are always positive enthalpies or bond energies because it's an endothermic process. And that really just means here that we have to put energy in to break the bond. So I've got this example down here of a chlorine element, which is 2 chlorine atoms bonded together, sharing 2 electrons between them. To break those chlorine atoms into just, that chlorine element into just 2 chlorine atoms, it'll require 58 kilocalories of energy for each mole of chlorine that I have. So that positive symbol is showing us that it's exothermic. And endothermic, and that's our enthalpy for that process. So here is a table of bond energies or enthalpies for different types of bonds to give you an idea of the amount of energy that goes into breaking it. And I'd like to draw your attention to a pattern that we see. So let's look at nitrogen. This is great because I have nitrogen with a single bond. And it takes about 163 kilocalories for every mole of that bond to break. A double bond takes 418 kilocalories per mole to break. It's a lot more energy. And that triple bond for nitrogen, 943. So as I'm increasing the number of bonds that are breaking between those 2 elements, it's not a linear increase in energy. Otherwise, that triple bond to nitrogen would be around, I don't know, it'd be under 600 kilocalories, but it takes more. And that's because these atoms, as we increase the number of bonds between them, are getting closer and closer together. So thinking some more about bond energies, we can come back to the enthalpy of the reaction. And I'm going to give you another way to calculate the enthalpy of reaction because that's secretly the theme of this entire quarter is how many ways I can teach you about enthalpy. And I think this is going to be number 5 or 6. So the enthalpy of the reaction, it can be estimated by comparing the cost to breaking old bonds to the gain in energy that you get from making new ones across a chemical reaction. So if I want to take the chemical reaction where I have CH4 plus Cl2, and I want to form CH3Cl plus HCl. What I'm going to be doing is breaking one of my carbon-hydrogen bonds. So I'm going to break one of these right here and separate that hydrogen. And I'm going to have to break this chlorine and chlorine bond as well. And so then these are separated right here. And then this one's going to come over and bond here, and this one's going to come and bond here. And so what I'm doing is I'm creating a carbon-chlorine bond, and I'm creating a hydrogen-chlorine bond. So what I'm doing is breaking a carbon-hydrogen bond, and I'm breaking a chlorine-chlorine bond initially to make this reaction happen. And to form my products, I'm forming a carbon-chlorine bond and a hydrogen-chlorine bond. All my other bonds stay the same, so I can just ignore them. It'll be the same on both sides. So what I can do then is calculate the enthalpy of the bonds breaking plus the enthalpies of the bonds forming, add those together and get an enthalpy of the reaction or an estimate of it. Which I should just do. So let's actually, I thought it was on the next slide. So let's go back to our table and calculate this. I'm gonna get rid of some of this noise right here. All right, so let's go find those enthalpies for these bonds. So to break something, it's going to be a positive enthalpy. So coming to our table, we need to find a chlorine-chlorine and a carbon-hydrogen bond. So here's my carbon-hydrogen bond and my chlorine-chlorine bond. It's a hunt is right here. And I'm forming a chlorine-carbon bond right here, and I'm forming a chlorine-hydrogen bond, which should be with hydrogen right here. So I'm going to take these values and put them down on the page we were working. So this carbon-hydrogen bond, since I'm breaking it, it has a positive enthalpy, right? So my enthalpy is positive, whereas when I'm forming it, it's going to release energy. That'll be a negative value for my bond energy. So my carbon-hydrogen is going to be a plus 414, and my units on that table were kilojoules per mole. My chlorine-chlorine bond is going to be 243 kilojoules per mole. Now, my carbon-chlorine bond, I recorded as, I'm going to go like this, 339 kilojoules per mole. And since I'm forming it, it's going to be negative. Then my hydrogen-chlorine bond is negative 431 kilojoules per mole. So now I'm going to take these enthalpies of bonds breaking and enthalpies of bonds forming. My enthalpies of bonds forming are always negative and my bonds breaking are always positive. I'm going to plug it in. So I'm going to take the sum on both sides, right, of this forming and breaking. So my forming ones, or sorry, my breaking ones are going to be 414 kilojoules per mole plus my 243 kilojoules per mole. Then I'm going to add to that my bonds that are forming, which are going to be negative 339 kilojoules per mole, plus my negative 431 kilojoules per mole. And by taking the sum of this, I'll be able to estimate the enthalpy of the reaction. I get an enthalpy of reaction that is negative 113 kilojoules per mole. So I've estimated the enthalpy of my reaction. It's negative 113, so this is a exothermic reaction. And it would actually give off heat. And you can see that here. We've got an exothermic reaction. And so we can use this to figure out our enthalpies of reactions by just looking at the bonds that break and the bonds that form.